let's take a look at a couple of examples that illustrate the second derivative test. So we're using the second derivative test to find local max or local min. Relative max, relative min, same thing. Okay, so the first thing we're going to do is find the first derivative. That's the same thing we would have done if we were doing the first derivative test. So these two are similar to start. The next thing we're going to do is also similar. We're going to set the derivative equal to 0. That is an effort to find the critical points where we have vertices. So I'm going to factor this. 3x minus 5, x plus 1 equals 0. That's the algebra. X equals 5/3. Also, x equals -1. Those are our critical points. So here's where it's different. The first derivative test would have us draw the no point number line, indicating where the derivative went from positive to negative, or vice versa. But now what we're going to do is find the second derivative, and that second derivative is 6x minus 2. And what I want to do is I have vertices at x equals 5/3, x equals -1, but I want to determine if it's concave up or concave down. So I'm going to evaluate f double prime at 5/3. So I substitute that in to my second derivative, and that's going to come out to be 8, which is greater than 0, which means concave up, but it also means vertex down. So therefore, f has a local minimum at x equals 5/3. Similarly, we're going to evaluate the second derivative at -1, and that's going to come out to be -8. That's only important because it's less than 0, and therefore f has a local maximum at x equals -1. I'm going to say it again that this is an area of confusion. People think f prime greater than 0, but that gets associated with a minimum. Greater than 0 is the concavity, but the vertex is down. Vice versa here, concave down, but the vertex is up. Example number 2, we have f of x equals 12 plus 12x squared minus x to the power 4. We're doing the same thing in this particular example. So first we're going to find f prime of x, which is 24x minus 4x cubed. We set it equal to 0 to find the critical points, to find the vertices. And I'm going to factor here. We'll pull out a 4x, and we're left with 6 minus x squared, and that equals 0. And you can see that there will be 3 critical points. One at 0, one at negative radical 6, and one at positive radical 6. Now I find the second derivative, and the second derivative is 24 minus 12x squared. I will evaluate the second derivative at the first critical point at 0. That's 24, that's positive, and therefore f has a local minimum at x equals 0. When I evaluate it at negative radical 6, or if I evaluate it at positive radical 6, both of those will give me the same value. 24 minus 12 times 6, 24 minus 12 times 6. I don't even want to bother evaluating. I can see that each one of those is less than 0, and therefore f has a local max at x equals plus or minus radical 6. In the third example, you might want to try this, press pause and then come back. You will notice that it is restricted to 0 to 2 pi, not including the endpoints. Okay, so we're going to find y prime of x equals the cosine of x. We're going to set that equal to 0. We need to find the critical points inside 0 and 2 pi. That occurs at pi over 2 and also at 3 pi over 2. The second derivative is equal to negative sine of x. The second derivative at pi over 2, that's going to come out to be -1. And the second derivative at 3 pi over 2 is going to come out to be +1. Therefore, y has a local max at x equals pi over 2, y has a local minimum at x equals 3 pi over 2, and of course you could have answered that without even having to done any calculus. That curve would have went like this. It's just the sine curve shifted up 3 units, and we can see that's going to occur x equals pi over 2, the maximum, and 3 pi over 2 for the minimum. But we showed that here using the second derivative test. Now we're going to revisit example 1 with a different set of instructions. I purposely put this set of instructions on a different page because you do different things depending on what is asked of you. In part A, it says use the concavity test to determine intervals in which the function is concave up. So let's do that. The first thing we need to do is find the first derivative. This is a repeat. We did this on the other example. But now we are not going to set that equal to 0. I don't care where the vertices are when it comes to intervals of concavity. So next I'm going to go right into the second derivative, which is 6x minus 2. Now I want to determine where the second derivative is positive, and I want to determine where the second derivative is negative. To do that, I set the second derivative equal to 0. And that's going to occur at x equals 1/3. That's not called a critical point. The critical point is when you set the first derivative equal to 0. This is maybe called a potential point of inflection. Its second derivative equal to 0. So now what I'm going to do is I'm going to repeat that process of no point number line. But this no point number line is going to be in reference to the second derivative. And on this no point number line, I'm going to determine the sign of the second derivative. So I'm going to plug a number to the left of 1/3, let's say 0. And if I do that, I see that I will have a negative value. If I plug a number to the right of 1/3, let's say 10, I see that I'm going to get a positive number. So this no point number line, even though it's not going to earn us any points on the AP exam, or my exam for that matter, it's going to help us to answer both part A and part B. So in part A, we're going to say f is concave up on the interval 1/3 all the way to infinity, and the reason for that is because f double prime of x is greater than 0 on this interval, and I can use that no point number line to make that determination. Next, in part B, it says find the point of inflection. So we're going to say that f has a point of inflection at x equals 1/3, and the reason behind that is because f double prime of x, not that it equals 0, but that f double prime of x changes sign at x equals 1/3. Yes, it was true that the second derivative did equal 0 at 1/3, but remember, it has to change signs to be a point of inflection. There's no point number line, knocked out 2 birds with 1 stone. Booyah. Same instructions for example 2. We're going to find where it's, concave down for part A, and we're going to use the point of inflection test to find points of inflection. Okay, we are going to first find the first derivative, 24x minus 4x cubed. Next, find the second derivative, which is 24 minus 12x squared. I'm setting the second derivative equal to 0 for potential points of inflection. And when we solve that, we get x equals plus or minus the square root of 2. I'm ready for my no point number line. Here it goes. There's my x-axis. I'm labeling negative radical 2 and I'm labeling positive radical 2. I'm going to determine the sign of the second derivative. If I plug a number between here, let's say 0, I plug that into my second derivative, and that is clearly positive. If I plug in something greater than radical 2, let's say 10, then it's 24 minus 120. That's clearly negative, and that also occurs to the left of negative 2. Our no point number line, but oh so important. Part A. F is concave down on open negative infinity to negative radical 2 in union with radical 2 to infinity, and that's because f double prime of x is less than 0 on this interval. And in part B, f has a point of inflection at x equals plus or minus radical 2 because f double prime of x changes sign at these x values.